Today we are discussing the average logarithmic dt. What is the topic of our discussion? It is the logarithmic mean temperature difference between the primary and secondary sides of a heat exchanger. Basically, it is the difference between the temperatures of the primary fluid and the temperatures of the secondary fluid. The value of the AVG, log. Temperature difference is one of the main values for determining the exchange surface of a heat exchanger. Obviously combined with fluids, global exchange coefficients, and a whole series of other factors. But I would say that it is a determining factor that often also helps to understand which type of heat exchanger is better to use. Allow me to clarify, it is significantly simpler to heat cold water using extremely hot steam that is readily accessible, as opposed to heating water that is already warm using slightly warmer water. If we need to heat water for a domestic heating system to 70 degrees C, and we have water available at 75 degrees C, everyone understands that it takes a long time. Why? Why are the two temperatures very close? If instead we have steam at 130 degrees, heating water to 70 degrees is easy. We have a primary heat source that is very hot. I had already talked about it before when I said that it is always better to have a high temperature energy source. That is a little very hot water rather than a lot of lukewarm water, for example, to recover heat. The concept is virtually identical. Plate heat exchangers enable working with narrow logarithmic mean temperature differences due to their significant advantages, as we have previously explained, of operating in perfect countercurrent and having a highly turbulent flow that enhances their heat transfer coefficients. For a shell and tube heat exchanger, the average temperature difference must be slightly larger. Otherwise, we have high exchange surfaces due to lower coefficients compared to a plate heat exchanger. If we even talk about APA collected exchangers, therefore air, water, or air-steam exchange, this average dt tends to widen even more. On the other hand, we have very high exchange surfaces. In essence, the average logarithmic temperature difference is inversely proportional to the exchange surfaces. The smaller the average logarithmic dt, the larger the exchange surface required to reach these temperatures. I will give you a practical example, and it's a case often found in our calculations. Let's assume we have water from a fridge unit arriving at 7 degrees. Fridges typically operate with a temp difference of 5 degrees, discussed in a previous video. Water from cylinder enters heat exchanger at 7 degrees, returns to refrigeration unit at 12 degrees. On the secondary, we aim to cool the processed water as much as possible. What is the limit? If we use a plate heat exchanger, the limit is 3 degrees with a log mean temperature difference of 2 degrees. Meaning, if fridge water on primary side is at 7 degrees C, we can achieve cooling temp of processed water on secondary side, process at 10 degrees C, 9.5 degrees C. 9 degrees C is already very high, to be honest. Calculations are made, but usually very high surfaces are obtained. If we had a shell and tube heat exchanger, this limit increases a lot. If our refrigeration unit is always at 7 degrees, what we can achieve on the secondary side is typically 12 degrees. That is at least 5 degrees more. If we want to lower it, we risk having to put more exchangers in parallel and in series, so a lot of surface area to achieve the same performance, therefore to achieve the same temperatures. The average logarithmic factor is extremely important when we size the exchangers. Remember that even half a degree has a highly sensitive meaning on the exchange surface and thus on the dimensions, i.e. on the cost of the exchanger. For more information, contact us. We'll provide calculation examples. Regards.